Hello everyone, welcome to topic 8.8, properties of buffers. By the end of this, you should be able to explain the relationship between the ability of a buffer to stabilize pH and the reactions that occur when an acid or a base is added to a buffered solution. As you learned in 8.4, a buffer is a solution that contains a conjugate acid-base pair. Buffers are able to maintain the pH of a solution when small amounts of acids or bases are added to the solution. Buffers are frequently used in fish tanks so that the pH of the water can be maintained. And another example of a buffer system is your blood. The buffering capacity of your blood means that the pH doesn't fluctuate. Your body's systems function best at a very specific pH because otherwise it'll mess with how your enzymes and your proteins perform their functions. So if we change the pH even just a little, it can impact your whole body system. And that's the same with water in a fish tank. If the fish tank becomes too acidic or too basic, it will affect how the fish in that tank, their bodies are able to do daily functions. Consume food, process the food, regulate everything. So pH is very important that it doesn't fluctuate, especially in living systems. If an acid is added to a buffered solution, the acid will react with the base in the solution, converting it to the acidic form. If a base is added to the same buffered solution, it will react with the acid, converting it to the basic form. This is an example of Le Chatelier's principle. Buffers are examples of solutions with common ions because you have your acid or base and its conjugate. So they're going to have the base part of the essential core part of the ion the same. Okay, consider a buffer that contains 2 moles of acetic acid. So in this case, the buffer is going to be acetic acid and its conjugate base is acetate, so something like sodium acetate, because sodium is always soluble. So doing a buffer with acetic acid and sodium acetate, you have your acid and its conjugate base, which is the acetate ion. And so those two will create a buffer system because we have something to donate protons and something to accept protons. And they both only differ from each other by a hydrogen atom. If 0.1 liters of a 0.1 molar sodium hydroxide solution is added to the buffer system above, it will react with the acetic acid to form the conjugate base as shown below. So since we're adding it, it is a unidirectional arrow because it is a reaction. And so we get this process, and we see that the addition of a small quantity of base, and this is 100 milliliters, to 2,000 milliliters or 2 liters of solution. So the addition of a small quantity of base has very little effect on the ratio of the conjugate base to acid. The same idea applies to adding an acid to a buffer system. So if we added the same amount of hydrochloric acid to the original buffered solution, it reacts with the acetate ion to form acetic acid as shown. The hydrochloric acid is strong and thus the limiting reagent, and the limiting reagent, so we can assume that it goes to completion and you have none of it left over. So the addition of a small quantity of an acid also has very little effect on the ratio of conjugate base to its acid. Okay, so let's look at writing acids and bases and conjugates, okay? So completing the table, and not below but to the right, with the conjugate acids and or the bases as shown. So we have our substance. So if we had the conjugate acid, that means we add a hydrogen ion, H2PO4 minus. And then if we have the conjugate base, that is going to be PO4 3 minus. Okay. If we look at the next one, we have water. The base, because the acid donates, so that means that the base is going to be -1 hydrogen ion. For the conjugate acid of fluorine, so this is acting as a base, I'm going to add a hydrogen to get a hydrofluoric acid. And the same with carbonic, or this hydrogen carbonate ion. If the substance is going to have a conjugate acid, it acts as a base and accepts a hydrogen ion, so H2CO3, so carbonic acid. But if this is going to act as the acid here, oops, okay, and this is a minus charge that's kind of small, it's going to donate that proton and form the carbonate ion. Okay. So now let's look at a buffer system composed of hydrosulfuric acid and its conjugate base, and how it is created by dissolving 3 moles of each into 1 liter of solution. Draw an image to represent the buffer system. Include spectator ions. You don't need to include water. So I went ahead and just drew 3 moles of my acid and not dissociated. And then I'm going to draw 3 moles of my conjugate base. But for every conjugate base I dissolve, I also have the sodium ion that's floating around as a spectator ion. Okay, so now we're going to write the reaction that would take place if a strong acid is added to the system. Well, the overall reaction or equilibrium is H2S plus H2O, and that's going to form H3O plus and HS minus. So this is our buffer system. If we add acid, it is going to react with the base. So we're going to have HS, and it's going to react with the acid, so H3O plus. And since it's a strong acid, it is going to go to completion, and these are aqueous. My apologies. So the base or conjugate base accepts a proton, becomes H2S, and that's aqueous, plus, and it accepts it from the hydronium ion, so it forms water. Okay. If we add a strong base, it is going to react with the acid. So pause the video, and I want you to take the same process where the acid of our buffer reacts with the strong base, and what does it form? Okay, and so you should have gotten that the acid of our buffer reacts with the hydroxide ion that was added. The hydroxide ion accepts a proton from it and forms water, and we are left with the conjugate base ion. Okay, so that concludes these notes. Work through the practice problems, check your work, and thank you for tuning in.